We're going to go over the Unit 2 force quiz right now. First question, give it a quick read. What you need to think about is this object is initially at rest. So we need to know, is it even moving in the first place? So to figure out if it's even moving in the first place, it needs to overcome the force of static friction. Now, that threshold force we always talk about would be this equation here. The force of static friction is equal to the coefficient of static friction times the normal force. Okay, the force of static friction is always equal to the applied force until this threshold is met, and then the force of friction turns into the kinetic force of kinetic friction. So this is how much force we have to overcome. Our coefficient of static friction is 0.5, and our normal force would be equal to the weight here, and we get 25 newtons. If 20 newtons is being applied, this object does not move. Looking at the next one here, I'm going to abbreviate this one just a little bit. It's an object sliding up an incline. I'm going to draw in the forces. We have Fg going down. We have friction pointing down the incline in the negative parallel direction. And we have the normal force perpendicular to the incline. From there, we have to figure out, okay, my acceleration is in the parallel direction, so I need to do the sum of my forces in the parallel direction. Might be a little hard to see here, but we do have, Fg has to be broken up into parallel and perpendicular components. So we additionally have Fg parallel and Fg perpendicular. Again, those shouldn't really appear on your free body diagram, but I'm just going to throw them in here for now. So to get the acceleration, that would be in the parallel direction. So the sum of the forces parallel equal mass times the acceleration in the parallel direction. My two forces in the parallel direction, I have a negative force of friction in the parallel direction, which they actually define as lowercase f. So we have negative lowercase f plus negative Fg parallel, which we should all know is mg sine theta. And that's equal to the mass times our parallel acceleration. And that ends up being our answer right here. Again, the force of friction they define as just being lowercase f. For this one here, we are looking for, the elevator is accelerating upward, and we need to find the magnitude of the force exerted on the top box by the bottom box. So we're looking at the first set of boxes here. So this box has two forces acting on it. It has mg going down, and it has the force of the bottom box acting upward on it. Now, is that also the normal force acting on it? Yes, but we're identifying it as being the force of the bottom box acting on the top box. Kind of like saying, what's the force of the ground acting on an object? That is the normal force, but we're being a little bit more specific here. So we know that the sum of the forces equals the mass times the acceleration. It is accelerating upward, so the acceleration is positive. That's sometimes good to denote that A is upward and positive. A sign there. So we have Fb plus negative mg equals ma. So Fb equals ma plus g. For this next one here, we are looking at the two boxes of mass m2. So we're looking at the third one. Okay, which of the following best represents the forces exerted on the bottom box? This is at constant speed, so we know that all of the forces have to cancel out now. So let's look at the bottom box. The bottom box here, of course, still has a force of gravity acting on it. We could call it mg, or we'll just call it Fg for now. think about what else is pushing on this box. The floor is certainly pushing up on the box, F floor, and it looks like the top box is going to be pushing down on it. So this would be the force of the top box, FB. So I did not draw this to scale, but you should have one force upward, the floor, and two forces downward, the force of the top box on the bottom box and the force of gravity. So our answer here would be this choice here. Notice that those are drawn to scale because these two forces downward should equal the force going upward because it is at equilibrium, it's at a constant speed. Number 5 is very similar to a question that we did. I think we did a lab, something like this. What we ended up finding in the lab was that delta x equals 1/2 at squared if the initial velocity is 0. Actually, let me go all the way back. Delta x equals v naught t plus 1/2 at squared. If the initial velocity is 0, we have that delta x equals 1/2 at squared. On an incline, a is equal to g sine theta. So we have delta x equals 1/2 g sine theta times t squared. So it's asked, how can we find theta? So we need to find the slope of the position as a function of square of time, or time squared. I don't really like the wording there. Why is that? Because we have y equals m times x. If this is on my x-axis, and this is my slope, there's my y-axis, we can use that slope to find theta. It won't directly give us theta, but we can use it to find theta. So this question ends up being a little bit math intensive. Understanding the concepts for this one and being able to do it without actually doing math is a bit more challenging. I'll try to talk through it. So let's look at what's happening here. So give the question a quick read. So in segment 1, you only have one force acting on the object. It's the force of tension pulling it. In segment 2, you have the force of tension minus the force of friction. And then in segment 3, it's just tension again. So the slope of this graph, this is very important, and you can't do the question without knowing this. The slope is equal to the acceleration here. And we know that the acceleration is directly proportional to the force acting on it. So if we look at segment 1, there's a positive acceleration. Segment 2, there's a negative acceleration. If we think about segment 2 for a moment, we would get a flat line if there were no acceleration, if there was no net force on the system, if the tension and the friction were equal. So if tension and friction were equal, segment 2 would be a flat line. There would be no acceleration because there's no net force, so it can't be that one. And actually, friction ends up taking a positive acceleration and making it negative. So friction has to be greater than tension. So I can eliminate choice A. And what else could I eliminate here? I cannot eliminate the other two. But at least now I have a 50-50 chance. So if you really, really, really get this stuff, you would recognize that if friction is twice as big as tension, this segment 2 would actually be like symmetric, if you will, to segment 1. It would be just as steep, but negative. So you can actually figure out right away that this would be the answer. Again, if it were answer D, segment 2 would look identical, just negative. How can we actually prove this, though? Well, what we can find is segment 1. Segment 1 has an acceleration of 2 and a mass of 0.5. So we know that the sum of the forces equals mass times acceleration. This is again for segment 1. So tension is the only force. The mass is 0.5 and the acceleration is 2. So we know that the tension force is equal to 1. All right, so how can we use that now in segment 2? In segment 2, we know that the sum of the forces equals the mass times the acceleration. Let me scroll down a little bit. We know that tension is 1, so we have 1 minus the force of friction equals the mass times the acceleration. We know that the mass is 0.5 and the acceleration here, I believe, is going to be negative 1.5. If you do the math here, you should get that the force of friction ends up being, actually, let me take a second because I don't want to mess it up. The force of friction ends up being 1.75 newtons. So not quite double the force of tension. All right, I kind of just did that in my head, so make sure I did that right, but I believe that's what it is. All right, so looking at this next one here, it says, what is the magnitude of the force of friction that is exerted on the block by the incline in segment 2? All right, just give me 1 second here. All right, so let's see what's happening here. So I want to see dash line shows. Okay, it's sliding up the incline in section 2. What's the magnitude of the force of friction exerted on the block by the incline? So let's quickly draw a free body diagram. We have, and I'm just going to abbreviate it a little bit. We have mg going down, sliding up the incline, so friction is pointing down the incline. And the normal force is going this way. So we have Fg perpendicular. This is going to be mg cosine theta. And we have, let me just see if I can fix this. We have mg sine theta. All right, so we need to find the force of friction acting on it. So in order to find the force of friction, we know that, let's see, force of friction is equal to, this is kinetic, mu times the normal force, but I don't know the normal force. So if I work in the y direction really quickly, or the perpendicular direction rather, I know that the sum of the forces in the perpendicular direction is equal to the mass times the acceleration in the perpendicular direction, which is going to be 0 here. My two forces in the perpendicular direction are just normal force minus mg cosine theta. That's equal to 0, so my normal force is equal to mg cosine theta. So going back now, my frictional force is equal to mu times mg cosine theta. Actually, it tells us for segment 2, it tells us right here that the coefficient is 2 times mu k. So this is just going to be 2 mu mg cosine theta. So for the next one, it's mentioning if the block is at rest on the incline. So if the block is at rest on the incline, our free body diagram is going to change slightly. If the block is at rest on the incline, we still have gravity pulling down, label that mg, and we still have the normal force perpendicular to the surface. But think about which way friction is acting. Friction is opposing motion. If it's at rest, friction is what's keeping it on the incline. It keeps it from sliding down. So our frictional force would actually be this way. Now let's add in mg sine and mg cosine. So mg sine theta would be this way, parallel to the incline. And mg cosine theta would be perpendicular to the incline. So you might be saying to yourself, well, the force of friction equation is going to be exactly what it was before. It's going to be answer choice A. But you need to realize something here. This equation for the force of static friction, okay, if I were to write it down right now, force of friction equals the coefficient of static friction times the normal force. This equation only holds true at the threshold of motion. And I give you a big hint here that we're not necessarily at that threshold. So we cannot use this equation. So what equation can we use? Let's use the equation for the sum of the forces in the parallel direction. Sum of the forces in the parallel direction equals mass times the acceleration in the parallel direction. This thing isn't moving right now. It tells us it's not moving, so that's 0. So in the parallel direction, it doesn't really matter which way you make positive or negative. I don't think they give us a distinction here. Let's make down the inclined positive, that's what I like to do. So I have mg sine theta minus the force of friction equals 0. So mg sine theta is equal to my force of friction. And that's actually it. And think about it for a moment. The force of friction is always equal to the applied force of static friction is always equal to the applied force up until it begins to move. So on an incline, the force of static friction will always be equal to mg sine theta until it's at the threshold. Then this equation is true. That equation is only true at one instance. Number 9, we did this lab. You just need a protractor. Number 10, we did this lab as well. Applying more horizontal force does not affect the normal force if you're on a flat surface, nor does it affect the frictional force. Okay, we did that with the simulation from PhET. So I gave you a really big hint here to draw a free body diagram for the bottom block. It looks like these two objects are accelerating downward. Okay, so if they are accelerating downward, A points down. There are two ways to do this question. You can either define downward as positive, or you can define downward as negative. I believe when we did this question, this is just like the forklift question we did. I think we defined downward as negative here, so I'll stick with that convention. Should probably do this in blue. Okay, so think about the forces acting on M there. If we were to draw a free body diagram, we would have mg going down and a slightly smaller tension pointing up. Tension smaller because it's accelerating downward, so mg has to be bigger. So sum of the forces equals the mass times the acceleration, T plus negative mg. Sometimes I just write minus mg, but it is a good habit to say you're adding negative mg, is equal to the mass times the negative acceleration because it's accelerating downward. I believe we need an expression for tension. So tension is equal to, if I bring over G minus A times M. So that'd be choice E. For this one here, this is more of a concept question, and treating this as a system can be really useful. Think about the net external force on the system before A crosses P. Okay, so I'm just going to put a little line down the middle here. Think about the net external force on the system before A crosses P. Your forces are going to be F0 minus the friction acting on A minus the friction acting on B. But once A crosses P, there is no longer friction between A and the floor. So after A crosses P, the acceleration of the system, or excuse me, the net force on the system is F0 minus the force of friction on B only. So in this case, the system will have a greater acceleration. All of the objects will, greater A value. If all of the objects have a greater acceleration, B has to have a greater acceleration. Therefore, how can B have a bigger acceleration? How can you give B a bigger acceleration? Tension has to get bigger. So the tension would increase. Again, because the two forces acting on B are only tension minus the force of friction on B. In order for the acceleration to increase, tension has to get bigger. It's going to zoom out a touch. And the last one here is we have acceleration as a function of applied force, not as a function of net force, as a function of applied force. Notice that if you were to draw a line of best fit here, it would hit at about 20. So the question is, why was there no acceleration for the first 20 newtons of force that were applied? The answer is an additional force was exerted on the object opposite of the applied force. Kind of like friction. Think about overcoming static friction. Now, what does the slope of this graph represent? If you said 1 over the mass, you are correct, but you may have oversimplified your answer. Remember that the sum of the forces is equal to the mass times the acceleration. There's actually 2 forces here. There's an applied force and a frictional force. And that's equal to the mass times the acceleration. Now, if I were to rearrange this, if I were to divide both sides by mass, I would get A equals the applied force over the mass minus the force of friction over the mass. If the applied force, now I'm going to break this up a little bit, I'm just going to rewrite it. The acceleration is on my y. 1 over m would be my slope. The applied force would be my x. And this is kind of interesting. The force of friction divided by the mass, this is actually my y-intercept. So y equals m. M can be confusing, but m means slope there. My plus b. This is my y-intercept. This is my slope, 1 over m. My x-axis is the applied force, not the net force. And my acceleration is y, on the y.